Hello everybody and welcome to another episode of your favorite algorithm channel. Today we're going to be doing LeetCode 22, generate parentheses. So this is the second parentheses problem we've seen. We had just recently done valid parentheses. So we understand what a valid string of parentheses is and what the nesting rules are. So I won't go into that in too much detail, but let's introduce the problem real quick. Given n pairs of parentheses, write a function to generate all combinations of well-formed parentheses. For example, given n equals 3, a solution set is, and then we have these five results. So these are all the possible combinations of valid parentheses. So n equals 3, well, that just means that we have 3 closing parens and 3 open parens at our disposal, and we have to use all of them. What I'd like to say about this problem before we get started is the code for this problem is actually not very complicated. This is more of kind of a logic problem. So I suggest when you are trying to solve this problem, just come up, what are the set of rules that need to be followed to construct a valid set of parentheses? If you can come up with a set of rules that form a well-formed string of parentheses, then you have everything you need to write this function. Like always, go ahead and try to solve the problem first. If you get stuck or you just want to see how I solved it, then check out the video. Otherwise, if you're ready to get started, come with me to the whiteboard. On the screen here, I have n equals 3, and we have 3 opening parens to work with and 3 closing parens. So what I want to talk about is a set of rules for ourselves that we can come up with to construct our string of 6 characters, or our valid set of parens. What are the rules that we have to follow to construct the string? If we can come up with the rules to construct this string, then we have written our function. Essentially, we have written our function. So let's say we're starting out with an empty string. Well, what can we add? We can't add a closing paren, right? Because no matter what we add after this closing paren, this string will be invalid, right? Because if we add, no matter what we add after this, well, there's our last character. It can't be valid because we're closing something off that doesn't have an opening counterpart to it. So that's invalid. And likewise, if we have to add a closing paren if our string is empty, right? We have to start, or sorry, not a closing paren, an opening paren. So we have to start with an opening paren in our string. So that's the first thing that we can take out of this. But also, if we have added an opening paren, we can do one of two things, right? We can add another opening paren, or we can close it, right? But what we can't do is we can't then add another closing paren. And why can't we do that? Well, because no matter what we add after this point, if we have added more closing parens than we have opening parens to match up with them, then no matter what we add after this, our string will be invalid. So the first bit of information that we can take in our function for constructing our string is that at any given point in time, the number of opening parens that we have must be greater than or equal to the number of closing parens that we have. So that's the first rule that we know that we have to follow when we're writing our function. And that's something we can be sure to follow while we're constructing our function. Well, what's another bit of information that's really important that we can take out of this or through our reasoning, right? So let's say that we're following this number 1 rule here, right? So we're adding an opening paren and we're adding a closing paren. Okay, so we add another opening paren, which means we can either add a closing paren, or we can add another opening paren, right? So we'll go ahead and add a closing paren, and now let's add another opening paren. Well, what do we know now, right? So we have added how many opening parens? Well, we've added 1, 2, 3 opening parens, right? Following this number 1 rule here, saying that we can't ever add a closing paren unless there are at least, or unless there are more opening parens, right? And here we can see that we've exhausted our number of opening parens at our disposal. So now we know that the only thing we can add is a closing paren, right? So our first rule here is stating that our opening parens must be at any given point in time greater than or equal to a closing paren. We cannot add a closing paren that makes this statement false. But the second thing we know is that if we have added all of our close or our opening parens, then we need to add we can only add closing parens, right? So if the number of closing, well, let me write that in an expression that's going to be a little bit better. So let's say that our opening parens have to be less than or equal to at any given point in time n, right? So these are the two rules that we have to follow to construct the string. Well, how do we know when we're done constructing the string, right? Well, that's simple, right? N equals 3. We have 3 opening parens and 3 closing parens. So we know we're done constructing our string. So our final rule is when the string length is equal to 6, right? Or we can say 2 times n, right? So if our string length is equal to 2 times n, then we're done, and we can store that valid string. If we follow these 3 rules, then we should be able to construct our valid strings. And now we just need to be sure that we're not duplicating them. Now, there are 2 strategies we can use to solve this problem. We can do this in a depth-first fashion, or we can do this in a breadth-first fashion. Now, I'm going to choose to do this in a depth-first fashion because it's more space efficient. And the reason why it's more space efficient is because, as you can see with these 2 rules, we need to keep track of how many open parens and how many closing parens we're using in our string so that we know what we can add or what's a valid add. What's the next, or what is a valid character to add in our next index in the string. So if we're keeping track of all of our opening and all of our closing parens in a breadth-first fashion, we have to keep track of a set, or we have to keep track of what it has been, how many opens we have used for every string. Whereas if we do this in a depth-first fashion, we only have to do this for a given string, right? So that is going to be more space efficient because we only have to keep our we only have to use the space of the call stack of size of n, right? The size of the string. Whereas if we do it in a breadth-first fashion, we have to do it in terms of the size of our answers, or the number of answers, which is going to be greater than the length of the string. I think in all cases. Somebody could prove me wrong out there, but I think in all cases, at least in most cases. So now that we have an idea of the logic we're going to use to solve this problem, let's just go through an example of what the function looks like. I'm going to show you what the function looks like, and then we'll just see how it executes. So now that we have discussed our rules for generating our valid combinations of parentheses, I've gone ahead and done something I don't normally do. I've just thrown the code up on the screen. So this is basically the code we're going to use to solve this problem. In fact, it's pretty much exactly the code we're going to use to solve this problem. I've kind of pseudocoded it a little bit. And what can we do in this function? Well, the first thing we can do is we can check to see, is our string the length of n times 2? If it is, then if we follow our rules, we know we have generated a valid string. So we're going to push it into our array. The second thing that we can do is if our open parens are less than n, then we want to add another open paren to our string. If our closing parens are less than our open parens, then we know we can go ahead and add a closing paren to our string. Now, the reason why I've thrown this code up on the screen is because we're going to be solving this in a depth-first recursive way. And I know you code ninjas out there are like, hey, recursion, no big deal. But us code karate kids, we got to do our wax on, wax off. We got to stay on the floor. And we got to understand how this code is actually running. So how we're going to do that is we're going to track the call stack. We're going to track the execution line in our code. And we're also going to keep track of our answers in the array down here. And we're going to be building the tree that this code creates at the same time as we're tracking the code that's running. So strap yourselves in. It's going to be a little bit of a long ride. If you're not interested in learning about recursion or how this recursive function works, then you can just look at the code and type this in and probably get the right answer. But I thought it would be beneficial to just kind of go through how this code is running. So the first thing we're going to do is we're going to push a call to genParen with an empty string onto our stack. And we'll move on to the next line. and our opens are less than n. So we're going to push another call of gen paren onto our stack with one open paren. We'll do that in our tree as well. And because we are going into the execution of another call of gen paren, we're going to start back at line 1. We're going to check the string. It's not n times 2. And we still have open parens left to use. Our open parens are not less than n. So we'll push another call with 2 open parens onto our stack, and we'll represent that in our tree, and we'll go into the execution of this function. We will check our string. It's not n times 2. We'll move on to the next line. Opens are less than n, so we'll push another call to to gen parens with 3 open parens onto our stack, and we'll go into the execution of this code. Our string is still not n times 2. Our opens are now equal to n, so we cannot add any more open parens. So we'll move on to the next line. Our closes are less than our opens, so we can push a call to gen paren with a closing paren added to our string onto the stack. And we'll go into the execution context of this function. Starting back at line 1, our string is still not the right length. Our opens are equal to n, so we can't add another one. Our closes, we still have some left to use because they're less than our opens. So we can push a call to gen paren with another open closing paren to our string onto our stack. And we'll enter the execution of this function. Our opens are equal to n still. Our closes are still less than our opens, so we'll add another one, pushing that onto our stack. And we'll enter the execution of this function call. So now our string is of length n times 2. So we can push into our answers array our valid string of parentheses. So we'll add that to our array. Our opens are still equal to n. Our closes are not equal to our opens, so we cannot add any more. And we're going to return from this function call, popping this off the stack. And now we're going to enter back into the execution context of what is ever on top of our stack. And where were we in our what line of code were we in when we last were in this execution context, when we were last in this function call? Well, if we look at our tree over here, we can see that this is the string that we generated at this point in time. And when we called gen paren from this execution context, we added a closing paren. So we know that we can return to that line in our function call. So we'll return to that line, and then we'll move on to the next line of code in that execution context. And we will return from that function call, popping it off the stack. And we'll check to see again, where were we? Well, we were in this function call, now on top of our stack. We were right here in the tree. We added a closing paren, so we'll return to that line, popping that off the stack. And we'll do the same for the next function call, popping this off the stack as well, because we added another closing paren. So we'll pop that off the stack, and we'll move back up our tree. So now we are here in our tree, where we have two opening parens. And now we can enter back into the execution line that we were on in this function call. Well, we were adding an opening paren. So now we're going to move on to the next line of code, where we are going to now check to see if we can add a closing paren. So we can. So we'll do that, pushing that onto our stack. And we'll enter the execution of this function call. Our string is not the right length. Our opens are 2, so we can add another one of those. We'll push that onto the stack, and we'll enter into that function call. Our string is not the right length. Our opens are now 3, so we can't add another one. Our closes are less than our opens, so we'll go ahead and add one of those, pushing that onto our stack, and we'll enter the execution of that code. Our string is not the right length. Our opens are 3. Our closes are still less than our opens, so we'll push another call to that onto our stack. And now our string, we've reached another leaf, right? So we're going depth first. We've reached the bottom of our tree again. Our string is the right length, n times 2. So we'll push that into our answers array. We'll go to the next line of code. We can't add any more parens, so we'll skip through all this. And we'll return from this, popping it off the stack. And we'll return to this function call here. And you can see where we were last time. We were here. We were adding a closing paren. So we'll move to the next line of code, and we'll pop that off the stack. And where were we in this function call? Well, we were adding another closing paren. So we'll move to the next line of code, and we'll pop that off the stack. And where were we? Here, with our string that looks like this. Well, we were right here. And what were we doing last time we were in the execution context of this function call? Well, we were adding another opening paren. So we want to return to that line of code, or that line in our code, and we want to move to the next line. So our closes are less than our opens, so we can add another one of those. We'll push that onto the stack, and we'll enter the execution of that code. Okay, our opens are less than n, so we'll add another one of those, pushing that onto our stack, and we'll enter the execution of this function call. Our string is still not the right length. Our opens are now 3, so we'll move on to our closes. We can close this one off, so we will push a call to that onto the stack. And we have terminated again in another leaf, and we'll see that our string length is n times 2. So we'll push that into our answers array, and we'll move to the next line. We can't add anymore, so we'll go all the way down, and we will return from this call, popping it off the stack. Looking where we were in our last function call, we'll return to that line, and then we'll go to the next line, popping that off the stack. And then we'll look where we were in our last function call here, where our string looked like this. We were here, so we were adding an opening paren. So we'll move to the next line, and we'll check to see if we can add another closing paren. We cannot, so we'll return from this call. And why couldn't we add a closing paren here? Well, because our closing parens in this execution, in the execution context of this function call, our string has 2 opening parens and 2 closing parens. So it does not satisfy this if statement. So we move on to the next line and we pop it off the stack. So now we return to where our string looks like this: 2 closes and or 2 opens and 1 closing paren. And where were we? Well, we were right here. And what did we just do? Well, we had just added a closing paren. So we'll return to that line, and then we'll go to the next line of code, which is to return from this function call and pop it off the stack. And now back up to where we have 2 closing parens. So now we have 2 closing parens. What was the last thing we did? Well, we added, or now we have 2 opening parens. What was the last thing we did? We added a closing paren. So we'll return to that line, and then we'll go to the next line of code, and we'll pop that off the stack. So now we're all the way back up to the top of our tree. So we had already explored the branch where we start with adding opening parens. And now we'll explore the other side. So we'll go to the next line of code, and we'll add a closing paren. We'll push that onto the stack, and we'll enter the execution of this function call. Our string is not the right length. Our opens are less than n, so we will push that onto the stack. Our string is still not the right length. We still have opens left to use, so we'll push that onto the stack, and we'll enter the execution of this function call. Our string is still not n times 2, so we'll move on. Our opens are now equal to n, so we can't add anymore. So we'll move on to the next line. We can now add a closing paren, so we'll do that, pushing that onto the stack. Our string is not the right length. Our opens are all used. We can add another close, so we'll push that onto the stack. And now we've terminated again in another leaf node. So our string length is n times 2, so we will push that into our answers array. And we'll move through our lines of code because we can't add any more parens, popping that off the stack. And we'll return to where we were when we were last in this execution context of this function. And then we'll move to the next line, popping this off the stack. And we'll do the same for all of these function calls until we get to this point here. So we last left off, that was right here. And we just added an opening paren. So we'll move on to the next line of code, which is to add a closing paren. We can do that. So we'll push that onto the stack. And we'll enter the execution of this function call. Our string is not the right length. We can add an open, so we'll do that, pushing that onto the stack. Our string is not the right length. We've used all our opens. We can add a close paren, so we'll do that, pushing that onto the stack. And now this satisfies the if statement. Our string is n times 2, so we'll push that into our answers array. And we'll move through our lines of code because we cannot add any more parens, popping this off the stack. And we will then just pop our way all the way back up through the tree until we get back up to the top. And now we're going to return our array. So in all of our previous function calls, we were returning the array, but it really didn't matter because we were just pushing our answers into our answers array, which is down here. This is the point that matters, that we're returning this array because we're in our final function call, and when we set this equal to a variable, we want to store this array in a variable somewhere. So in our final function call, where our string is empty and our opens are 0, we have explored both branches of our tree, which have given us all of our possible combinations of valid parens. And we will now pop this off the stack returning the array and storing it, hopefully, in a variable, or returning it as our answer, of course, I guess. I hope that was useful. I hope that was beneficial. It definitely helped me when I was learning recursion to kind of go through it line by line like this. So JavaScript is single-threaded, and what that means is every time we hit a line of code, we cannot move on from that line of code until we've resolved it. So every time we make a function call like this, when we recurse, we have to go into the execution context of this function and resolve it before we can move on to our next line of code. And I think going through this process, anytime you're trying to figure out recursion, just going through the process of following the thread, the single thread, through all the execution context and the different function calls will help you understand how to write better recursive functions and just understand recursive functions in general. In the next section, I will quickly go over the time complexity. I don't completely understand it, so I think we can just look in on it together, but I can give you a short little explanation of what it's all about, and we can make some statement about it. All right, I'll see you in the next section. So we did go over the space complexity a little bit earlier, but I just wanted to put this on the screen. So this is the time complexity of this problem, and I'm just kind of like waving the white flag here. I want to apologize to my friend Dakota, who spent a lot of time proving this to me. I wanted to prove it to you guys, but my math proof skills are not quite as advanced as his. But I will say that this time complexity is exponential in nature, and it's based on, so the input is generating the nth Catalan number. So you can see here I've drawn on the screen on the bottom here, this is the beginning of the number sequence of the Catalan number. So this is what we would get if we were to put our parens in. So if we put in 0 parens, there's one arrangement for that. If we put in 1 paren, I guess there'd be one arrangement for that. And then it goes from 2. So the set we went through was 3, which is 5. And then it goes to 14, 42, 132, 429, and so on. So the Catalan number sequence, if you're interested in learning about it, I'm going to check it out. I just couldn't figure it out in time to explain it to you guys. But yes, this paren problem is a pretty famous problem that's representative of the Catalan numbers, which gives you this time complexity 4 to the n over root n. So if you guys have figured out how to prove this in a really easily understandable way, please leave a comment on my video and reach out to me and let me know how you did it. Anyways, let's see what this problem looks like in code. So the first thing I want to do is define some default parameters. So we want to pass in a string. We'll just define that as an empty string. Then we're also going to want to pass in how many open parens we're using, and we'll set that to 0 to start with. And then what else do we want? Well, we also want to pass in an array to store all of our answers. So we'll do that. So the first thing we want to do is we want to store a variable or create a variable of closes. How many closes do we have? Well, that's just going to be the string length minus our opening parens. And then if our string dot length, if it is equal to n times 2, then we want to push that into our array. So we'll do array.push, and we'll pass in our string. So what's the next condition? Well, we want to say that if our opening parens are less than n, then we want to make another call to generate parentheses. And we want to pass in the same arguments, and adding to our string, we want to add an opening paren, and we want to increment the number of opening parens that we have used. And we'll pass the same array in to catch all our answers. So what's the other condition we want to fulfill? Well, if our closing parens are less than our opening parens, then we know we can make another call to generate parentheses. And we'll pass in the same arguments, but this time adding to the string a closing paren. We won't increment the opening parens, and we'll pass in the same array to catch our answers. And then at the end, we just want to return the answer, so we'll return the array. And that's pretty much all there is to it. So I'm going to run this, see if we have any bugs, and we don't. And look, I get this terrible runtime. I'll run this again. Still pretty terrible, but we'll go ahead and take a look at the answers. and I'm going to look at some of the other solutions and see how it compares to what we wrote. Let's look at the best solution. Well, here we have it. So it looks pretty similar to ours, right? They're passing in the string, and then a left and right paren, and then the results array. And what they're doing is they're just saying that if left is less than n, so in our case it would be if open is less than n, then then make it call to generate parentheses, adding an opening paren and incrementing left. And then they're saying if right is less than left, then make it call to generate parentheses and add a closing paren. So it's pretty much the same as ours. So I figured, hey, let's just rip this and see if it's better, if we get a better runtime, because I've run it so many times, I haven't been able to get the good runtime that makes me feel good about myself. So we'll just see how the best submission on LeetCode is doing right now, and it gets the same. So our submission is just as good as theirs. That's all I really wanted to prove. But I think the main focus of this is really more the logical reasoning. I mean, this is pretty much 3 lines of code. So it does a lot of work, but it doesn't take a lot of code to do all that work. It's more of a logic-based kind of problem. Anyways, I hope you learned something from this video. I hope you learned something about recursion if you weren't a code ninja already. And I hope to see you in the next one.